Hi, everyone. Small crowd today, as I thought it might be post-midterm, and I understand that a number of the students in the class had other midterms yesterday as well. We're going to continue talking about the Laplace transform and use it to answer some interesting questions about boundary forcing. And I'll give you maybe some insight into the Laplace transform in its sort of full glory, which you may or may not have seen before. And after that, we're going to start talking about time harmonic forcing in the interior and the boundary. I think I've warmed you up for that with some of the discussion we've had so far and some of the assignment questions. I did notice from the assignment questions that some students were not yet up to speed with the sort of background approach that I had hoped you would have had. So I'm going to backtrack a little bit and fill in some of those details. And then we'll look at some time harmonic forcing in the interior and boundary conditions and see how that goes. Okay, so let me share screen. And let me minimize my window so I can see the Slack channel in case I miss comments from the chat. Okay, let's have a start. We're talking about the Laplace transform. Right, so we've got a function f of t. And we take this sample of it for every s. And you can think here of s as being a complex number. And out pops the Laplace transform. And we're going to have various techniques for finding the Laplace transform of some functions we're interested in that solve partial differential equations. And we want to take the Laplace transform and work out what the corresponding function is. And that really happens with tables at this point in this particular class. There's some asymptotic work that you can do with the Laplace transform as well, which we won't cover in Math400. Just as an example, right? I wrote out a longer table last lecture. You can see it in the notes. But if you start with something that grows exponentially, simply, you end up with a transform which has a simple pole at A. And remember, let's suppose that A is positive and real. Then this thing is only defined for values of s with the real part bigger than A. But this transform seems to be defined everywhere except at A. And it comes from this transform defined on the region that it's defined with complex continuation, which you should remember from earlier classes, Math400. That's the sort of flavor of this thing. And one of the ones that we'll use today is if you start off with the complementary error function. And what's this function? This is our friend. It would be our friend if we were statisticians. It's the tail end of a Gaussian distribution, scaled in a way that makes this this distribution have a weight 1. So, okay, maybe I'll say that note. Earth C at 0 is 1, right? So you've got this Gaussian, it's the tail weight of that Gaussian. Like I said, this is something that comes up naturally in probability and statistics courses, which you may or may not have taken. I took 1 statistics course as an undergraduate where this sort of stuff came up. What are the things that make the Laplace transform? This L is encoding taking a function and making its Laplace transform. This is where it's useful for solving ordinary differential equations, and you'll see we'll be able to make use of it for PDEs as well. And then another property which we talked about last time is if you take the Laplace transform of a convolution, you get a product of Laplace transforms. And this is something which we're going to read backwards. We're going to find some Laplace transforms of things we're interested in, which you can see is a product of 2 things for which we can understand what the Laplace transforms are. And then we'll recognize the solution we're interested in as a convolution. We've seen this before with the Fourier transform, and it turned out that one of the functions here was the data, and the other one was a Green's function, right? So we had the convolution of the data with the Green's function giving you the solution. And we'll see some things like that happening here. Again, I'm not sure out there, but it's a pretty small audience, right, today. So I'm not sure out there, even in the small elite group, for whom the Laplace transform is their friend. And I really don't know, because I can't ask, who will be watching this video later for whom the Laplace transform is their friend. So let's do some simple examples. So let's do some ODE examples. Depending on the ODE course that you took as an undergraduate, you will have seen the Laplace transform or not. Okay, so let's look at an ODE for U of T. The Laplace transform only works for linear constant coefficient problems. Only works as well as what I'm going to show you on those kind of problems anyway. And they always have to be linear. I'm going to give initial conditions. Laplace transforms are rarely used for boundary value. Well, okay, no, that's not true. I'm gonna do some stuff with boundary values with Laplace transforms. Okay, so this is a pretty easy one, right? You could write down the solution was A cosine t plus B sine t, and from the initial conditions, you could work out that it was cosine t. So we know what the solution is going to be. Right? So let's take the Laplace transform of this. Right, so if I take the Laplace transform of the time derivative of u, right, then I get s times the time derivative of u minus the time derivative of time 0. That's just using this property, but on f double prime. Right, and then I have to take the Laplace transform of u, and I get 0. Okay, now I'm going to do it again. Right, I can have s squared times the Laplace transform of u minus S times the initial conditions. Then I've got this term. And then I've got this term. Right, so I'm going to call this U tilde. U tilde. I know that this is 0 and this is 1. And if I put that all together, I'm going to get f squared U tilde plus U tilde minus 1 is 0. That gives me U tilde is S minus S. Okay, I was going, hey, where did the S go? S over 1 plus S squared. And then I look up in tables for this transform, and I see that U of t is cosine t. So a number of you who I know can use Laplace transforms, you can solve problems with forcing this way, as long as they're, sort of reasonable level. And you can use this technique to solve problems that you could have solved with method of undetermined coefficients. Now, I'm a method of undetermined coefficients fan, so that's the way I do it. But if you're more comfortable with the algebra with the Laplace transform, it's just different algebra getting to the same solution, then that's something that the Laplace transform can be useful for. Okay, and just to go back and look at one of our things that we started with near the beginning of term, let's use the Laplace transform to get a formula which will involve convolution for U of t that solves the following problem. This is going to be a constant plus f of t. I'm going to look at this one with the data, but no initial conditions. Remember, we can always divide this up. The initial conditions will give you exponential behavior. And we've already seen a form of the solution of this, but it'll come out from the Laplace transform. So we already know this was our first look at Duhamel's principle without really looking at it in its general case, just showing that this is what happened for this one. So we know the formula that should come out is this. You integrate the forcing term pretending it was initial conditions at that time and propagating it forward. So let's see that formula come out with the Laplace transform argument. So I'm going to have S U tilde minus the initial conditions, but those are 0. And over here, I get A U tilde plus F tilde. Now it's just algebra, right? This is another one of these things where our game has been, we reduce PDEs to ODEs. And in this game, right, we're reducing ODEs to algebra in Laplace transform. And so here we get U tilde of S is F tilde of S divided by S minus A, right? And let me write this as F tilde of S times 1 over S minus A. So it's a product, which means U is a convolution, right? So it's a convolution of the data with the inverse transform of 1 over S minus A, which I know is e to the AT, right? And so I get U of t, it's a convolution all right, same formula we had before. So this is another way to derive it. Okay, so Laplace transforms turns ODEs, as long as they're constant coefficient and linear, into algebra. And then there's potentially difficult work of deciphering from what comes out, the Laplace transform sitting there, right? Deciphering what comes out into using tables or Wolfram alpha into what the original function is. So doing the inverse transform. I think there's a question coming through. Convolutions in this case, yeah, it's exactly where this is the convolution that comes out from the Laplace transform. Now, you could think of these as going from minus infinity to infinity, but remember, when you think of something coming from the Laplace transform, the inverse transform, it's 0 for negative arguments. Okay, and if you've got a function that's 0 for negative arguments, then this is the form that you get. So yes, but no, because of the feature of the Laplace transform, this is the window that you get. This is something that actually comes with sort of tricky uses of Laplace transforms. Oh, I can scroll there as much as I want. Let me scroll here. If you look at this, right, it's not clear, right, just from this expression, right, that future f values can't affect previous u values, right? But then if you look at the details of the convolution with this, you know, negative values for, or 0 values for negative arguments, then you get this, and you always have causality assured in these arguments. Okay, I don't know who asked that question, but is that answering it? Are we dealing exclusively with one-sided Laplace transforms in the course? I believe there are only one-sided Laplace transforms. Once you talk about you know, transforms from minus infinity to infinity, you're talking the Fourier transform. Okay, so let's do a Pde example. This is a, you know, sort of fun one. We can talk about the sort of the physical motivation behind it. I could put something over here, a boundary condition over here. I'm talking about the heat equation. I'm going to have the heat equation in a semi-infinite domain, just so that we can do the algebra. So I'm going to have ut as uxx. And I'm going to give initial conditions are 0. Right, so this is the typical thing. And now I'm going to give some non-zero boundary conditions. Remember, this is our last problem piece that we're looking at. I'm going to give you just temperature 1 over here. Now, you do sort of need some information, right, on this side, some boundary information on this side. So there's a far field condition. In the notes it said hidden condition, but it's really the far field condition, which just said u of x and t goes to 0 as x goes to infinity, right? Because you've started with 0 temperature here. You got some stuff coming in from this side, right? But far away, right? You're not gonna see that, right? So this is the condition that we want. And you notice this is mathematically interesting, not so physically interesting, right? You can imagine that this is an idealization of, your rod, which you're heating up, and it was at 0 temperature, and you suddenly attach it to something that has a higher temperature, and you watch how that temperature enters into the domain. But mathematically, you have to look at this corner, and this is called the space-time corner, which makes it sound like it's like some sort of science fiction thing, right? Okay. It's the space-time corner. It's just where the initial conditions meet the boundary conditions. And you notice there has to be a discontinuity here. So the thing that's going to come out of this has got to be a weak solution, right? Oh, pardon me. Hay fever. Okay, so let's have a look at what comes out of this thing. Okay, so let's take the Laplace transform. Okay, and now maybe I should, be a little bit more careful with what I say, right? Now I'm saying take the Laplace form in t for every x. So I've got a time derivative. So when I take the Laplace transform, I'm going to get s times the Laplace transform minus the initial conditions, but they're all 0, right? So I'll get s times the Laplace transform. And then I'll get the transform's derivative in x. I'm assuming that the solution is smooth enough that I can do all of this. And you'll see that a sensible weak solution comes out. And so I'll say that in this course, that will be the justification for it. Now, this is a different game than we've seen before, but it's the same kind of game, right? So the game has been with PDEs that we turn them into a set of ODEs, an infinite set. So for every S, right, this is an ODE. So it's a sideways game to what we played before, but it's the same sort of idea, right? Now remember, we're thinking of S as being a complex number. And so I'm going to write a solution, but of course we're going to have to worry about the square root of S, which is going to appear in this expression, right? I'm going to have a constant. Well, this constant will depend on S. I should put that in, right? It's going to be e to the minus square root of S times x, and then there'll be a positive square root. Right? So remember, if I'm looking in the real S plane, I'm thinking that this solution is going to be bounded, right? Which means that the Laplace transform is really defined for every S that's got positive real part, right? So this is where I'm thinking of it, right? And even more than that, I'm going to think of S as being on a line, something like this, okay? And this, you'll see why I do that coming up. And so if I've got S on this line, right? And I want to take its square root, right? Well, and of course there's two roots, right? I'm going to define, let's say that this thing is getting really close to the imaginary axis, but not quite. So that's a complex number that's almost at 90 degrees. And so I'm going to have some s, square root of s over here. This is the one I'm going to take as the positive root, right? And then I'll have the negative root over here. And now you can see with that definition of square root that this solution, I can't have this solution because u has to be bounded as x goes to infinity, and that's not bounded, right? That's got e to the positive real part times x and some imaginary stuff as well, possibly. But this has to be 0 by the far field conditions. Right, and when I take the transform, this is, you know, if I take the transform of 1, right, I get 1 over s, right? So if this is going to match up, this is the boundary conditions, right? I've got this, I've got these boundary conditions, u is identically equal to 1. So that tells me u tilde of x and s is 1 over s e to the minus square root of s times x. Okay, now I'm going to look back at my table. Where did it go? Yeah. Oh, I never told you what the, I never reminded you what the Laplace transform was. Okay, let's go back and look. 1 over s e to the minus square root of s. Okay, so this thing, except for this x, is looking sort of close, okay? And now I have to introduce another property for the Laplace transform, which is how it gets scaled. This is very similar to the property for the Fourier transform, which I don't think we mentioned. If I've got a constant c, so this is a property of the Laplace transform. If I've got 1 over c f of t over c, that gives me the transform of c times s. And so if I've got this thing, and I want to write it like something I can match to the transform. Remember, I know what the transform of 1 over s e to the minus square root of s is, right? So I want to have c to be x squared, right? Right? So I've got to do a little bit of work, right? I want to write this thing as, remember, I'm talking about the transform in, it is just a function of x or s for every x. So in this game, x is a constant. So I'm going to have a 1 over, what am I going to have? I want to have 1 over s times x squared, so that I can have an e to the minus s times x squared. So I can use this idea. But then I have to multiply by x squared to make it the same as it was before. Right, and so now I can use the table for this transform with c is equal to x squared, right, to get oh, hang on here. What is the transform again? Let's go back. Let's go back. Now I have to be, I'm getting a little bit confused. Anyway, in my notes, what I've got is this. This is C. In my notes, it's okay. Oh, yeah. Okay, yeah. I'm going to have t replaced by t divided by c, but t comes in with the square root. Okay, so that's what was confusing me. You've got an x over 2 square root of t. Okay, so let's remind ourselves what the error function looks like. Right, I know it, here's the graph. Maybe I'll say an argument y instead, because I'm going to put y is x over the square root of t in and show you what things look like as a function of x for different values of t. So this is something, right, which starts off at 1, and then you're integrating out the tail of the exponential, and so it goes to 0. Right, so that's the function. Now let's see how this behaves as a function of x for different t. So now I'm going to have x. I'm going to have u as a function of x and t for different t. Right, for t small, right, I'm scaling the argument to be something that starts at 1 but decreases rapidly to 0. So this is for t small. Right, and then for t large, I'm extending this out a long way. It looks like this. Right, and now you can see that this matches up with your intuition for what should happen with this problem. Remember, physically, this was the rod that has some heat conduction going on in it. And it started off at time 0 with a u identically equal to 0. And then right away, you start you put it in contact with something at a higher temperature, right? And as you leave it in time, of course, at the beginning, you just heat up a little bit, right? Right, and then if you've left it for a long time, then you've heated up further into the interior, and of course, the scaling for how the heat penetrates into there with this square root of t behavior. That's an interesting application observation, which of course you could get from experiments, but this is a much cleaner way to see that kind of scaling of this kind of behavior. Okay, so we've used the solution almost looks like characteristics on the curve x is equal to the square root of t. well, let's not talk about characteristics in in the context of the heat equation. Let's say that that is the self-similar variable. I don't know if you've ever heard the term self-similarities in differential equations. It's usually not talked about until graduate level courses in math, but you may have seen it in physics courses. So yeah, there's a self-similarity of behavior with x over the square root of t that's coming from these kind of systems. And again, that scaling is interesting to applications. Okay, so I'm going to take an aside, which is, well, it's Math400, right? I think you guys are all old enough to hear that what I'm going to show you now is not testable. It's just to complete your education, right? If you've never seen it before, what's really going on with the Laplace transform? Okay, so I'll spend just a few minutes talking about that, and then we're going to go on to the next topic, which is time harmonic forcing. Okay, so I'm going to go back to the beginning. Let's just think of the scalar case. And it's defined for t bigger than or equal to 0, and it satisfies that it could have exponential growth, but it's got exponential growth at a bounded rate, right? And so this is going to be true for all t bigger than or equal to 0. Okay, so now let's consider an alpha. This is going to be real, or an eta, that's bigger than a, right? And so I'm going to look at g of t. I'm just taking the function, multiplying it by a negative exponential so that it actually goes to 0 in a nice way, and I can talk about its integrals, and still 0 for time less than 0. And then I'm going to notice that g is G, let me phrase this differently than in the notes, has a well-defined Fourier transform. Right, you can integrate it, right, because it's decaying exponentially, right? So it's all good, right? So let's talk about its Fourier transform. Right, so this is, well, my function 0, right, for t less than 0, so I don't get the full integral. And over there, it's just this thing. And so this is just 1 over 2 pi, the Laplace transform of S, with S is equal to eta plus I alpha, right? So now you can see why, when I was talking about where I'm thinking of S as living in the complex plane, it's on a line far enough this way, right? So that the real part's big enough so that when you multiply by that negative exponential by the thing you're trying to take the Laplace transform for, it all makes sense, right? So the Laplace transform is just an integral, right? That's defined on for S in the complex plane, but the only thing that matters is that you got it on a vertical line in the complex plane, right? So we've got the inverse Fourier transform. Which would say that g of t, that's the thing that had the transform, right? That's f of t e to the minus eta t, and this is defined for t bigger than or equal to 0. This is just the inverse Fourier transform. That's g hat of alpha e to the, okay, I got a minus here, so I'm going to have a positive sign here. I got the 1 over 2 pi here, so I've got a 1 here, d alpha. And so f of t, I can say is 1 over 2 pi, the integral of minus infinity to infinity, right? Well, now I'm going to put in this Fourier transform is equal to this Laplace transform. So I'm gonna put that in there. This is going to be f. This is the Laplace transform on this line. And then I've got an e to the eta plus I alpha t d alpha. Right, and you'll notice this is the same complex argument. And so I can really think of f of t as being a integral on this contour. So it's a complex contour integration. Right, this is the inverse Laplace transform. I take the transform on those values. And then I've got e to the zt. I've got dz. Well, okay, now I have to be a little bit careful. As I look at that contour, dz is I d alpha, right? So to make it work out, instead of 1 over 2 pi, I've got 1 over 2 pi I over here. And so this is really the way to think of the Laplace transform. If you want to go beyond, you know, transform, right? You can find it in tables, right? But if you want to have a theoretical understanding of the Laplace transform, it is something which you define on a contour that's far enough to the right in the complex plane so that you dampen out any exponential growth that you have in the solution. This is why the Laplace transform is only defined for functions that have bounded exponential growth at worst, right? And then if you want to do the inverse transform, then you do this contour integration on that. And then there's all kinds of math 300 techniques that you can use for contour integrations. The page says Fourier transform. Should it say Laplace? Where's that? Still going up? Okay, now I'm confused. I mean, I've showed a relationship. G has a well-defined Fourier transform. Yeah, I want to say Fourier transform there. Yeah. F has a Laplace transform, and I'm showing the relationship between the Laplace transform and the Fourier transform. Who should get more credit? Now that you realize they're both the same idea, one of them is just sort of turned sideways. Okay, good question. I don't know the historical answer to that one. Okay, so untestable, because this is not Math400, I'm not going to ask you to do contour integrations, even for a part B question, I don't think. But I just remember as an undergraduate thinking, why are you making me learn this Laplace transform? It's all about, table lookup, right? That doesn't seem interesting. When all the table lookups I could do instead with method of undetermined coefficients and solving constant coefficient problems, which I can do, with the characteristic equation, and so on. But this is why, right? And there are some approximation tools that come out of this, which can give you a lot of insight. Probably studied in Math450 perturbation methods, although I don't know for sure. Okay, so what I said I would do next was to start talking about time harmonic forcing. And to backtrack a little bit, okay? Because I've noticed in assignment questions where I assumed some knowledge from students that it wasn't always there. Okay, so I'm going to talk about just time harmonic signals. What do I mean by a time harmonic signal? I mean a pure frequency so sinusoidal periodic signal. So I'm talking about with frequency omega. So this is actually angular frequency. And to get the actual frequency, there's a factor of 2 pi, which I always have trouble working out where the 2 pi goes. So I won't try here, okay? So a general signal like that, I'm just talking about a scalar quantity. You've got some constant times a cosine term and some other constant times a sine term. Okay, and often what you want, right, is to put this into an amplitude phase form. Okay, again, I know a number of students know this. Okay, I also believe I have evidence that there are some students that don't know this, so that's why I'm doing it. So this same signal can be written in a number of different ways, right? And one of the ways you can do it is to say, I want to know what the amplitude of the signal is, right? And it's going to be a cosine term, but with some phase change, right? So it'll be not a cosine wave, it will be shifted over an amount, okay? Okay, and you can use trig identity, which is that cosine of alpha minus beta is cosine alpha cosine beta plus sine alpha sine beta. To work out that if you start with this kind of form, right, that you can match them up if you've got C is a cosine this phase shift, and D is a sine of this phase shift. And A naturally comes out now as the square root of C squared plus D squared. And delta is the angle from the positive x-axis to the vector CD. Now, I could say it was the arctangent of C divided by D, except that won't always get the right quadrant, right? And so you guys do know some complex variables, so I'll say that the delta that you want to pick, this is like atan2 in MATLAB or Fortran. Okay, no one uses Fortran anymore, sorry, right? Right, so this would be the argument of C plus ID, right? So if you're over here, right, if the vector CD is here, right, then that's pretty clear. But, you know, you could also have a CD over here, right, in which case delta would be that angle there. And that comes out of this complex argument thing. This complex argument one gives a phase angle that is between minus pi and pi. Oh, and here's something interesting I found, right, teaching engineering courses. Every type of engineering and different sciences have a different standard form for signals, amplitude, phase, right? Some of them want it in sine instead of cosine, and some of them want plus delta instead of minus delta. So, okay, just as a warning, depending on what group you end up working with, you may have to retool what you think of as amplitude phase form. Okay. Oh, the other thing that can change is sometimes they want delta going from 0 to 2 pi instead of minus pi to pi, right? So if you work with different groups, you may have to do some extra conversion. Okay, so that's one form. Another form, and this is the complex form that has appeared in solutions. And what I encouraged you to use, because it simplifies the algebra in many cases, is the real part of something that has a complex amplitude, e to the I omega t, right? And the complex amplitude is going to be C minus I d. And so the magnitude of A, so the complex magnitude of A, this is A, this is the amplitude. Right, so complex amplitude is kind of a nice way to write things. Again, we're doing some review before we work on some PDE examples with time harmonic forcing. In fact, maybe today I won't get to the PDE examples, and we'll look at those next time. So let's look at a scalar Ode example. Okay, let's find a particular solution. u of t to u double dot plus u dot minus u is equal to 0. Okay, and I want to make a point here that I've been making a few times with assignment questions, but let's hammer it home in this setting. As a little bit of an aside, we're going to find a particular solution, right? Let's as an aside, let's find the homogeneous solutions. Remember, this is a game where you try, because it always works, things that look like e to the RT. You get r squared plus r minus 1 is equal to 0. That gives me r is minus 1/2 plus or minus the square root of 1/4 plus 1. Okay, I wanna change my equation. Okay, now plus u. So this is a minus 1. Okay, hang on. Okay, right, so this is minus 1/2 plus or minus I times the square root of 3/4. Right, so I have a decaying oscillatory homogeneous solutions. The important thing is these decay. So when I find the particular solution, right, and just depending on how you find the particular solution, right, it could have some components of the homogeneous solution in it, right? I want to find the particular solution, and there's the way that we do this is the natural way, right? I want to find the particular solution that has none of these decaying parts in it, right? Oh, I'm finding a particular solution. I haven't put the forcing in here. This is so it. Okay, the aside was doing the equation as I actually wrote it. I want to have sine 2t, which is going to be a minus the real part of I e to the I 2t. Right, so I want to find the solution which, right, I'm forcing it with this oscillatory pattern. It's going to have a response which is oscillating with this period or angular frequency 2, right? And that's the only thing I care about. We've seen problems like this before, I think, on previous assignments and even the last midterm. And we can't call the thing that we're interested in a steady state because it's not, right? Because it's got this oscillatory behavior. But it's the limiting behavior as time goes to infinity of the solution. We don't care about this, right? Not interesting. Okay, the only interesting thing about it is the time that it takes that transient to die away. That could be interesting. And then if you need to take into account that transient, then you'd look at the frequency of these oscillations. But if you're only interested in, hey, how does this thing behave for much later times, it's only going to be the particular solution with this frequency responding to this this input that you care about. Okay. Oh, and hey, we could use Laplace transforms to solve this, right? I'm not a Laplace transform guy though, right? So now I just want to plug this in. and go, I want u of t. I know it's going to be, this is the particular solution now. And remember, when you talk about the particular solution, you can add any amount of homogeneous solution, and it's still a particular solution. So I'm interested in the particular solution, which doesn't have any of that exponential decaying stuff in it. So I want to have this as the real part. It's going to be some amplitude, e to the I2t. Right? And in fact, I can drop this stuff off and I can solve the u double dot plus u dot plus u is equal to minus I e to the I2t. Then I'm going to get a solution that looks like this, and I can just take the real part and afterwards, because the real and imaginary parts of the solution don't mix. Okay, so I'm going to put this expression in here. I'm going to get everything on this side is going to be multiplied by a complex A. Now, of course, because I've changed the equation to make it decay, my notes aren't going to match up, and there's some calculations at the end, which I'm not going to do because I'm not going to try and do those thinking on the fly. I don't think well on the fly. Okay, in fact, I can say everything is going to get multiplied by e to the I2t. It's going to be some stuff, and then I'm going to have minus I e to the I2t. And again, this is a nice game that we've played before at reducing problems to simpler problems. Here I've got an ODE, which I'm going to reduce down to some algebra, right? So when I take the second time derivative here, I get a factor of -4. When I take the first time derivative, I get a factor of 2 times I. Now I've got 1. Is all equal to that. Now I can see these are all it's just an equation for the coefficients, those terms. I get A is minus I over -4 plus 2I plus 1. Okay, and so now you can write this out in complex form, and then you can go back to this thing and fish out the real and imaginary parts, if that's what you want to do. And again, what's in the notes is all of that work for the original problem before I changed it so that it would have exponential decay, so I could talk about this other feature. Okay, what are we looking at? We got 9 minutes. Okay, I think we can quickly do this. So let's look at a heat conduction problem. With a time harmonic interior forcing. All the details are in the notes. There's some technical stuff at the end, which I'm not going to look at. Okay, so here, right, I'm going to have my usual Dirichlet conditions. And I've got my Pde in here, and I'm going to have some initial conditions here, which I talk about, right, in the notes before we get to the nitty gritty, right? But let's say we were only interested in the periodic in time behavior after the transient from U0, right? This is the thing with the sine series for the heat equation, all of which decay exponentially in time. And so all the stuff from the initial conditions isn't going to matter later on. Again, we have this behavior which we can't call a steady state because it's still got time dependence, but it's the limiting time behavior, right? So what we would want to do is to take U is A, complex A, E to the, what period did I give? Oh, sine t, so E to the IT, right? This is what we want to solve for, right? Okay, and so now we could put that into this equation, right? And we would have I times A, E to the IT is equal to A double prime, E to the IT, minus X times 1 minus X E to the IT. It's I'm doing this a little bit differently than in the prepared notes, because here, right, we were looking at sine t. So we could write this as, you know, I e to the it with a minus sign and say plus, and say we want the real part. But in fact, because we want the sine t forcing, I'm going to say we're going to work this out, and what we want is the imaginary component is u of x and t. Something I remember from teaching Math 152 students, so you're probably well beyond this. When I say the imaginary component of a complex number, I mean the real number that multiplies I, right? So the imaginary component's not imaginary, right? It's the real part that multiplies I. Right, so now I'm going to have a pretty simple ODE. It's simple, except, you know, it's got a little bit of complexity, right? I've got A double prime minus I times A is equal to, which way did I do this now? It's minus X times 1 minus X. Right, and I've got to have A of 0 equals 0 and A of 1 is equal to 0. Right, and now you can see that I'm really being complex, right? Now I have to do the auxiliary equation, right? I can still take A of x as e to the rx, right? But now r squared minus I is equal to 0. And so this gives me r is plus or minus the square root of I, right? So now you have to look at the complex plane, right? You're going to have the square root of I is going to be 1 plus I over the square root of 2, right? Hey, the square root of I came up in something else we did, but I can't remember what that was. Something relatively recently.
I can only imagine that it was really complex.
Okay, so now I can go a of x. Now I'm just going to use the method of undetermined coefficients, right? I know that I've got c e to the 1 plus I over the square root of 2 times x plus d e to the minus 1 plus I over the square root of 2 times x plus a plus bx plus cx squared. This is the method of undetermined coefficients. Right, so this is homogeneous. This is particular. And you can do the game, right? So you find A, B, and C first to match the right-hand side forcing terms, right? The minus x plus x squared terms, you can match with these guys. And then afterwards, you pick C and D to match the boundary conditions, right? Because these could give you some non-zero contributions at the boundary, which the homogeneous solution has to fix up, right? And then, right, you'd have to go back to the a of x e to the I t, right? And you'd have to find the imaginary component, right? Okay, and that would give you the solution. And like I said, this is all in the notes. This is all in the notes. Okay, so I'll just do dot, 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 because it's 1044. This, the detail, just the details are in the notes. It's a Math 215 problem, except it's got complex numbers in it. So, okay, maybe not Math 215, but it's the same kind of process. Time harmonic. Okay, so if you needed a little bit of a primer on these harmonic functions and the different representations, and how using complex exponentials can simplify the computations. You don't have to keep track of sine and cosine anymore, or cosine and phase variable. It's all encoded in complex arithmetic. So next time, we've got one last main topic, which is we're going to do a time harmonic forcing on the boundary. We're going to do it with the heat equation and the wave equation. And then I don't think that'll take the whole lecture. And then we're going to start on free boundary problems. We'll talk about the Stefan problem is the easiest one to start with. That is, you've got water that's freezing into ice, and there's a moving interface between the ice and the water that you can put into a Pde modeling format in a sort of idealized way. All kinds of interesting things to do about that. Okay, that's gonna end. Oh, there's a question. which is that the A0 and A1, actually all you need them to be is purely real. So remember, when you go to this complex form, you're really solving two problems, right? You're solving the problem for the real part and the problem for the imaginary part. So you're solving the sine of t forcing and the cosine of t forcing. You're doing it both at the same time. If you're going to separate out the imaginary component, then yes, but I think that just makes the problem harder. Now you have to match sine and cosine terms instead of just these complex exponentials. So I think it's easier to choke down a little bit of complex arithmetic to solve both problems at the same time. Okay, 10:48. I'm going to stop.